Okay, let's dive in. So imagine something that can just zip right through the entire planet, like a ghost through a wall, basically.
Yeah, that's pretty much the picture for neutrinos. They're incredibly elusive.
And these ghost particles, they've apparently sent us a pretty wild message from way out there in the cosmos.
That's right. The KM3 Net telescope, which is, an amazing piece of kit in itself, it detected one.
A neutrino.
But not just any neutrino, right?
Yeah.
The energy levels were, what was it? Something staggering.
Oh, absolutely staggering. We're talking 16,000 times more energetic than anything we can manage, even at the Large Hadron Collider.
Wow. Okay. 16,000 times.
Mm-hmm. And what's really fascinating, is that their ghostly nature, their ability to just pass through almost anything,
Yeah.
means they carry information straight to us from places light might not even escape. So this detection at this energy, it's opening a new door. Definitely sounds like it. So for everyone listening, if you're curious about this kind of cutting-edge science, the universe's biggest puzzles, but maybe don't want all the super dense jargon.
Uh-huh.
That's what this deep dive is about today. We're going to explore, what makes these things tick, how this detection happened way down under the Mediterranean,
Up underwater.
and why it's such a big moment, all based on the great info from our sources.
Okay, so to start, maybe just a quick reminder about neutrinos themselves. They're fundamental particles, the absolute basic building blocks.
Smallest Legos, kind of?
Exactly. Can't be broken down further. And they have almost zero mass and, crucially, no electric charge.
Ah, no charge. That's the key to the ghostliness, isn't it?
That's it. They just don't really care about electromagnetic forces, which, govern how light and most other stuff behaves.
Right. And wasn't there a quote from Rosa Caniglione, something about them being messengers?
Yes, a really good one. She said, they are special cosmic messengers that reveal the secrets of the most energetic phenomena in the universe. Really captures it.
It does. These tiny things just cruising across the universe, ignoring all the dust and gas that would block light.
Precisely. That's why they're invaluable. They let us peek into places we just couldn't see otherwise. Think about the core of an exploding star.
A supernova.
Yeah, or right near a supermassive black hole. Light might be trapped, but the neutrinos, they can just stream right out, carrying, the pure signal.
Incredible. Okay, so how did they actually catch one? Especially one this energetic, down there under the sea. Tell us about KM3 Net. Must be huge.
It is huge, and it has to be. KM3 Net Kilometer Cube Neutrino Telescope. It's this massive observatory deep in the Mediterranean. The sheer volume of water, eventually a whole cubic kilometer.
A cubic kilometer?
That's your detector, basically. You need that much target material because neutrinos interact so rarely. This specific one, caught on February 13th, 2023.
Okay, but how do you see it? It's not like it flashes a light, is it?
Not directly, no. But there's an indirect effect. See, when a super high-energy neutrino like this does occasionally smack into an atom in the water, it can create another particle, a muon.
Muon, okay.
Now, this muon is charged, and it's moving incredibly fast, faster than light in water.
Ah, okay. Faster than light in the water, not faster than light in a vacuum. Key difference.
Crucial difference, yes. And because it's breaking that local speed limit for light in water.
It creates like a shockwave.
Exactly, a light shockwave.
Yeah.
It's called Cherenkov radiation.
Yeah.
Think of the sonic boom from a jet, but with light. It creates this faint cone of light.
Cherenkov radiation. That's the blue glow you sometimes see, right? Like around nuclear reactors.
That's the exact same phenomenon, yes.
Yeah.
A charged particle outrunning light in that specific medium. KM3 Net is basically built to spot those faint flashes.
So what does it actually look like down there, this giant detector?
Well, picture hundreds of vertical strings like cables anchored to the seabed and stretching upwards, 230 of them right now. And along each string, you have these spherical glass modules, 18 per string. One source called them high-tech Christmas ornaments, which is kind of a fun image.
Ah, high-tech ornaments. And inside them?
Inside each sphere, you've got 31 photomultipliers. Think of them as super sensitive light detectors. They can pick up even a few photons in total darkness and amplify the signal.
Got it. So the muon zips past, makes the Cherenkov flash, and these photomultipliers catch it.
That's the idea. And by seeing which detectors light up and when, scientists can reconstruct the muon's path, and from that, figure out the original neutrino's direction and, importantly, its energy.
And it's getting bigger.
Yeah, the plan is to expand it out to that full cubic kilometer volume. More volume, more chances to catch these things.
Just incredible engineering. So this specific detection, why is it so special? We've seen neutrinos from space before, haven't we?
Oh, we have, yes. We've detected neutrinos from the sun, from nearby supernovae, even some from further afield. But this one, it's all about the energy.
The P's you mentioned.
Exactly. This is the first one ever seen in the hundreds of PeV range. PeV is petaelectronvolt.
That's well.
It's 10 to the power of 15 electron volts, a quadrillion.
A quadrillion. It's hard to even picture that.
It is. And like we said, 16,000 times the energy of LHC collisions. At these kinds of energies, you might be seeing physics, particle interactions, maybe acceleration processes that are just beyond what our current theories have fully explained.
So it's like tuning into a completely new frequency.
That's a great way to put it. A frequency we didn't even know was playing, potentially revealing whole new cosmic process.
Right. And Pascal Coyle, who was the spokesperson for KM3-Net then, he said it opens a new chapter in neutrino astronomy. Sounds pretty bold.
It does, but honestly, in this case, it's justified. It really is a new window. We're now probing energy scales in the universe with neutrinos that were just off the map before.
Like Galileo pointing his telescope up for the first time.
A bit like that, yeah. A whole new way of seeing, potentially leading to who knows what discoveries.
Okay, so we caught this super energetic ghost. The million-dollar question then, where did it come from? What could possibly make something like this?
That is the question, isn't it? What kind of cosmic engine can accelerate particles to these insane energies? We have some prime suspects based on what we know.
The sources mentioned supermassive black holes, right?
Definitely high on the list, especially the ones at the centers of active galaxies, active galactic nuclei, or AGN.
Right, those incredibly bright galactic cores.
Exactly. You've got matter swirling into the black hole, creating these incredibly chaotic, powerful environments. It's thought they can act as colossal particle accelerators shooting out cosmic rays, and maybe these ultra-high energy neutrinos as a sort of byproduct.
So the neutrino could be like evidence of that acceleration process.
Precisely. And Yuri Kovalev from the Max Planck Institute for Radio Astronomy, he stressed combining these neutrino detections with other observations, light, radio waves, etc., to try and connect the dots between cosmic ray acceleration, neutrino production, and what these giant black holes are actually doing.
Makes sense. Multi-messenger astronomy, they call it.
Exactly that. Okay, so besides black holes, what else could do it? Maybe exploding stars, supernovae.
Supernovae are definitely another strong contender. Those explosions are unbelievably energetic. They're known particle accelerators, too. So this neutrino could have been born right in the heart of one.
Plausible. And then there's that other idea, cosmogenic neutrinos. Sounds a bit more out there.
Yeah, that's a bit different. The idea there is you start with an ultra-high energy cosmic ray, maybe a proton that's already flying through space.
Okay. And then it interacts with the cosmic microwave background. You know, the leftover radiation, the afterglow from the Big Bang, that's everywhere.
Right, the CMB.
So the cosmic ray hits a CMB photon, and that interaction could, theoretically, produce a super high energy neutrino.
Wow. So direct from a black hole's neighborhood, maybe from a supernova, or maybe created out in deep space from something else hitting the Big Bang's echo.
Pretty much covers the main theories right now. And, you know, the big caveat is this is just one detection at this energy level.
Right. Hard to draw firm conclusions from a single data point.
Exactly. We need more. We need to see if more neutrinos arrive from the same patch of sky, for example. Unlike cosmic rays, which get bent by magnetic fields, neutrinos travel straight. So, in theory, they point right back to their source.
Ah, that's a key advantage. They're like cosmic pointers.
If we can catch enough of them, yes.
Amazing. Now, KM3-Net isn't alone in this hunt, is it? The sources mentioned Antares as well.
Correct. Antares is another neutrino telescope, also in the Mediterranean, a bit smaller than KM3-Net.
Yeah.
It really helped pioneer this deep-sea detection technique and found cosmic neutrinos, too. Paved the way for KM3-Net, really.
And then there's something completely different, like the Pierre Auger Observatory, that looks for cosmic rays, not neutrinos, right?
Right. Auger, down in Argentina, tackles it differently. It looks for the highest energy cosmic rays, mostly protons. When one hits the atmosphere, it creates a huge shower of secondary particles.
An air shower.
Yep. And Auger detects these particles using this massive array of water tanks spread out over a huge area. The particles entering the tanks also produce Cherenkov light.
Oh, it's Cherenkov again. But in tanks on land, not the deep sea.
Exactly. So Auger detects the aftermath of cosmic rays hitting the atmosphere using water tanks, while KM3-Net looks for muons created by neutrinos interacting deep in the sea. Different messengers, different methods, but both aiming to understand these extreme cosmic accelerators.
It really shows you need all these different approaches, doesn't it?
Absolutely. It's a multi-pronged attack on the problem.
And speaking of multiple prongs, KM3-Net itself sounds like a huge collaboration.
Oh, it's massive. Truly international. The collaboration involves, what, over 360 people? Scientists, engineers, technicians, students from 68 places in 22 countries.
That's a big team.
It takes that kind of effort for something on this scale.
And it's actually 2 detectors, isn't it? RCA and ORCA?
That's right. 2 main parts in different locations. IRCA, that stands for Astroparticle Research with Cosmics in the Abyss, is off Sicily. That's the one primarily looking for these high-energy astrophysical neutrinos, like the one we're discussing. It uses taller detector units spaced further apart.
Okay, RCA for astrophysics and ORCA.
ORCA, Oscillation Research with Cosmics in the Abyss, is near Toulon in France. Its main job is studying the neutrinos themselves, specifically how they oscillate or change type as they travel. So it has shorter detector units packed much closer together for finer detail on lower energy events.
Got it. So RCA is the wide net hunter for the high-energy beasts. ORCA is the close-up inspector for neutrino properties.
Nicely put.
Yeah.
Different designs for different science goals, but part of the same overall project.
And the sources mention specific German contributions, too, from universities and Max Planck.
Yes, definitely. Researchers from Erlangen-Nuremberg, the Max Planck Institute for Radio Astronomy in Bonn, and Würzburg University were all key players. It really highlights the strong German expertise in this area and, again, the collaborative nature of the whole thing.
Good to see that kind of international teamwork. There was also mention of a project called MUSES. What's that about?
Ah, yes, MUSES, Multi-Messenger Studies of Energetic Sources. That's an initiative backed by the European Research Council, really digging into those active galactic nuclei, the AGN.
The black hole engines again?
Exactly. MUSES is all about combining the neutrino data with other signals light across the spectrum, maybe even gravitational waves eventually, to get a complete picture of what's happening in these incredibly powerful objects.
So bringing all the cosmic messengers together.
That's the essence of multi-messenger astronomy. You learn so much more when you can see or detect an event in multiple ways simultaneously.
Fascinating. Okay, so let's try and wrap this up for our listeners. We've gone deep into these ghost particles and this really amazing detection. What's the big takeaway here?
I think the main thing is that this single detection, this ultra-high energy neutrino seen by KM3NeT, it's genuinely a landmark moment. It gives us a brand new tool, a new way to look at the most extreme events the universe throws at us.
A new window, as you said.
A new window into energy regimes and cosmic processes we just couldn't access before with neutrinos.
And as we discussed, it's probably just the beginning, right? This one event is exciting, but the real payoff comes with more detections.
Absolutely. We need more data points to start tracing these things back to their sources, to really understand the physics of cosmic acceleration and maybe even uncover totally new phenomena. This detection is like a very loud knock on a door we've just opened.
A loud knock from a ghost particle, so maybe a final thought for people to mull over.
Well, just consider this. These almost massless, almost non-interacting particles are traveling across billions of light years, potentially from the edge of supermassive black holes or exploding stars, carrying information directly to us deep under the sea.
Undisturbed, uncorrupted information.
Exactly. So, as we get better at listening, at catching these faint whispers from the cosmos, what other secrets are they going to tell us? About the universe, about the fundamental laws of nature, maybe even about our own place in it all.
It really makes you think, doesn't it? What else is hidden in those whispers?